Good afternoon, everybody, and welcome to the CISL seminar. I'm Jeff de la Beaujardière, the organizer of the seminar series. Today, we're very happy to have Dr. Joe Hammond speak to us about Zarr. Dr. Joe Hammond is a scientist at NCAR and CDG, but he's also the technology director at the nonprofit Carbon Plan. His work focuses on the development of data and software tools for applications across the geosciences. He's an active contributor to numerous open source software projects, including X-Ray, Dask, and Zarr, and is a founding member of the Pangeo project. For my group personally, Joe was very helpful in our first project to convert the CESM large ensemble dataset to Zarr and put it in the AWS cloud. Joe holds an MS and a PhD from the University of Washington, a BS from the University of Arizona, and a PE in Washington State. Joe, whenever you're ready, I think you can share your screen and go. Thank you.
All right. Audio check. Can someone confirm that they can hear me?
Sounds good on the Zoom.
All right. We'll just present. All right. You ready to go? Well, hi, everyone. Yeah, so as Jeff mentioned, my name is Joe Hammond, and I am indeed a project scientist in CGD in the terrestrial sciences group, and I also have a side gig which is actually taking up most of my time right now at a nonprofit called Carbon Plan. Today I'll be talking about Zarr, which is a data format and a set of programming libraries for working with multidimensional array data. And I thought I'd just start with some important business of sorting out what title to use for this talk. So the flyer went out with the title, "What's all the fuss about Zarr?" So some of you might have heard about Zarr and been wondering a little bit more about it. And so this talk is for you. The more traditional title for this talk would be, Zarr, scalable storage of multidimensional array data for parallel and distributed computing. It's a bit of a mouthful. Since most of us are probably sitting at home doing our social distancing thing, I thought I could have gone with Zarr for NCAR from afar. I'm in Seattle, so I'm not even in Boulder presenting to you. We could get a little more punny. We could go with Zarr, you ready to rumble? It's a playoff season in the NBA, so maybe that one makes you laugh. Anyways, I think the chat feature in the streaming service we're using should allow you to add your own punny titles to this talk. Zarr kind of lends itself to this sort of thing, so hopefully that gets you going.
Actually, the poll feature in the Slido for
okay. There you go. There you go. All right. So outline for today. I'm going to give a little intro about myself and my connection to the Zarr project. I will provide a fair bit of background and motivation to why Zarr exists and what problem it solves. I'll hit the well, not 30,000 foot, but maybe 10,000 foot level overview of what Zarr is. We won't touch every single nitty-gritty detail, but we'll cover a lot of them. And then I'm going to highlight some applications of Zarr in the wild and look at Zarr applications and cloud computing and HPC applications, recent additions to Net Cdf, and some more kind of far out frontier ideas. So I already said some of this. I wear a couple hats. I'm at NCAR part-time. I work at this nonprofit called Carbon Plan, doing data and policy work around the climate problem. I helped found the Pangeo project in 2016 and have spent a lot of time doing open source development on projects like X-Ray and Zarr and Dask. So this is my contact information on the social medias. You can also find my email, I'm sure, at NCAR. Before I go any further, I should stop and say that I'm just one little cog in an otherwise incredible machine of developers that have worked together to create Zarr. So currently there's more than 40 open source developers that have made contributions to the Zarr Python library. And there are a bunch of Zarr client libraries, which I'll cover in a bit. So the community is actually much larger than 40 developers. I want to give a special thanks to especially Alistair Miles at Imperial College of London, who created Zarr originally, and Ryan Abernathy. I stole some slides from both of them for this talk, or at least some graphics. So I really appreciate them putting their stuff out there and making it available. Jeff for setting up the talk, and then both Kevin and Dennis provided input on various aspects of this presentation. All right, so jumping into it on the motivation, I mostly work with climate data. I assume most people that are listening to this work with climate data that looks similar to this. So it's very commonly multidimensional arrays. And so in this figure, I'm showing a data set that is a collection of variables. In this case, it's temperature and precipitation. They're data cubes. So they have 3 dimensions, X, Y, and T. So that might be longitude. Those X, Y, and T might be the dimensions that represent longitude and latitude. Longitude and latitude might also be their own coordinates. So for those of you that are familiar with Net Cdf, the Net Cdf data model, this figure will look quite familiar to that data model. And in fact, this is what a lot of our climate models, CESM, the CMIP6 or CMIP archive would look like. And this is kind of a foundational concept, I think, that a lot of you should be familiar with for those of you that work with climate data in the present day. So this is our starting point. Goes probably without saying, but we've been making a lot of data lately. And so this is just one example. This is the size of the CMIP archives over time, or over generation. And you can see with CMIP 5, the collection grew to over 1 petabyte. And the final estimate of CMIP 6 is yet to be fully quantified, but could be as much as 20 petabytes. Talking about very large data sets, and the growth of those data sets has really kind of spurred on the development of a new set of kind of tools and approaches for working with really large climate data. Well, what do we do with our data? Well, everybody takes the mean, right? We take the average across multiple dimensions or axes of our data. And that's how we calculate things like the global mean surface temperature. We also analyze the variability. We might take the standard deviation across one of the dimensions. And so this is an example from the analysis that we did with the CESM lens data set that's on AWS in Zarr format. We'll come back to that. Of course, everybody is doing machine learning these days. And so we want to machine learn with our data. And here's an example from the Berkeley lab identifying atmospheric rivers. All right, so the problem statement, let's boil it down a little further. We can actually generalize the problem statement that Zarr is trying to tackle even further than climate data. We have some computation we want to perform, and we have inputs and outputs that are both multidimensional arrays. So I've got some data cubes, I'm going to do some computation in the middle. And we've got a few problems that we face. The first is that the data we're using is larger than the memory capacity of our computer, so cannot fit the input or the output arrays into RAM. And so we need to come up with some way to process the data or store the data in intermediate steps. Sometimes the computation that we're doing can be parallelized. Some part of it can be parallelized, or if we're lucky, the problem might be embarrassingly parallel, where there's no relationship between the individual blocks of computation. We often run into the fact that I/O, or input-output of data from the storage layer, is the bottleneck. So when the complexity of the computation is moderate or trivial, you end up spending a significant amount of time for an individual computation just doing the reading and writing of your data. That bottleneck might be because of limited I/O bandwidth. The file system, for example, could be slow, or the input-output might not be parallel. So we might, the store that the data is in might only allow serial reads or writes. The fourth part of this problem is that data can be compressed, and we often want to compress data to either improve I/O bandwidth or to improve the amount of data we can store on disk, or to limit the amount of data we can store on disk. I just note that compression is a very active area of innovation right now, and there's lots of moving, the field is still moving forward. And one part of the Zarr project that's really cool is it makes it really easy to try out new compression methods. The final piece here is that speed matters. In the world of working with big data, the velocity in which you can go through this cycle of exploring rich data sets via interactive analysis, and then make hypotheses and test and repeat is really important. So this is actually what got me started in this space. I was working on my PhD, where I was, this was 10 years ago. I was developing a regional climate model where I was generating terabytes and terabytes of data, and I just found that the process was, for analysis, was just too slow to be productive. And so I ended up starting to work on the X-ray project, and that's what got me sucked into the rabbit hole of working on data science tools like I do now. So speed is really important, and it gets to be more and more important as the data gets large and the processing time increases. So this is the problem summary we have. We've got multidimensional data. It's larger than memory. Some of that computation can be parallelized. I/O is a problem we need to be thinking about, as well as compression. So the general solution won't surprise anyone here. It's not particularly new, is that if we can combine a chunked parallel array computing framework with a chunked parallel array storage framework, we can align the chunks, we can get a pretty long ways towards accelerating the applications we use multidimensional array data with. You might be sitting there, hopefully you're sitting there asking, don't we already have containers for multidimensional arrays? And of course, the answer is yes. We have the HDF5 container, Net Cdf. Net Cdf4 is built on HDF5. There's Grib, there's GeoTIFF, there's Parquet. There are more. But, and this is why we're here, they're limited to in one way or another. So some of these are limited to POSIX style file systems. They might be limited to lower dimensional data. GeoTIFFs tend to be 2 or 3D maximum. Parquet is tabular data, for example. Or they might be only support single-threaded access, which makes parallelization difficult. So all of these have challenges, and Zarr is trying to fill the space there a little bit. So what is Zarr? Zarr is an open source format for the storage of chunked, compressed, n-dimensional arrays. It was designed to support storing large multidimensional arrays, large both in volume but also in rank, in the number of dimensions. It supports parallel reads and writes, and that depends somewhat on storage medium or the storage layer that you're writing to, but Zarr is designed to support parallel reads and writes. Pluggable compression and filters. So there's, as I'll explain in a bit, there's a layer between the in-memory data representation and the storage representation, and that the data passes through in Zarr a layer of compression and filtering. And finally, flexible storage systems. So we don't just use POSIX file systems anymore. The cloud computing has become a really important architecture, and Zarr was designed with cloud computing in mind. Finally, the specification for Zarr is community developed and it's open source, and that's a really valuable feature that many of the other data sets I mentioned are either more mature or they aren't community developed. So it's a bit of an awkward thing to teach, to give a seminar on a data format. So I thought I'd walk through some examples using the Python API to Zarr to help describe a little bit more about what the data model is and what Zarr does. But I'm not going to go super deep into the Python API. Not everybody listening is likely a Python user. So the Python application that I'll be showing will be merely to highlight some of the data model components. And I've listed 3 links here for how you can go deeper and learn more about the various applications or the interfaces to Zarr. So grab these links. So obviously the slides will be available later on as well. Okay, so the focus will be on Zarr Python for now. We'll come back to other languages in a bit. So Zarr Python was the initial, and it has really become the reference implementation of the Zarr specification. It depends on NumPy, which is a very widely used numeric computing library, and a library called NumCodex, which is also developed by the Zarr developer team. It's easy to install. Here are the documentation, websites, and the GitHub page to go find more. Okay, so we'll start with the data model. The data model for those that are listening that are familiar with Net Cdf or HDF5, Zarr uses a very similar hierarchical data framework. So, multiple arrays, they can be created and organized into a hierarchy of groups. So in the figure I'm showing here, we have 2 arrays, one called foo, one called bar. They each have 6 chunks in them, or at least we're showing 6 chunks. And we know these arrays happen to be 2-dimensional because the keys are 2 digits, 2 digits long. So 0, 0, 0 would be the first chunk along each of its 2 axes. The chunks are compressed, so each individual chunk is compressed, and they can be decompressed individually. They're not compressed all as one. There's metadata associated with each of the arrays and with the root group. So the group is the top level data set. It has a Z group and a Z adders key, and then each of the arrays have a Z array and a Z adders. So I'm going to come back to what all these do, but this is the basic data model. You can have groups inside of groups. I'm not going to go into that today, but you can do a fully nested hierarchy as well. All right, so here's our first bit of Python code that I'll be showing. So we'll import NumPy and import Zarr. And I'm going to start by creating a directory store. The directory store is going to lay out the chunks and the metadata files in a normal POSIX file directory. And that's going to allow us to kind of look around them and actually interact with them a bit in this talk. there are, as I'll cover in a bit, there are multiple different types of stores. The directory one just happens to be the easiest to work with for this. So we create a store. We'll call it example1.zar, and that and then we'll pass that store to the group constructor, and create our group root. And that all that did was create a directory called example1.zar and created our metadata keys .zgroup and zaddrs. There's nothing really here yet, so we have to go on and create our first array. Here we'll create the foo array. We'll tell the array that its shape should be 3000 by 2000, and the chunks should be 1000 by 1000 each. So if you do some quick math, you'll see that we'll end up with 6 chunks in a 2x3 layout, just like the figure on the right shows. Then we'll see that the total number of bytes is 22, almost 23 megabytes. But we actually haven't written any data to disk yet. But we've set up the structure to do that. So created our first variable called foo. It's worth stopping and taking a look at the Z array file inside of foo. So here, this file is just JSON. It's just a JSON object, and so we can just use the Unix cat method to take a look at this, and we'll see that we'll see all the same metadata that we just wrote, and a few defaults that I didn't specify. So the chunks are 1000 by 1000. The shape is 3000 by 2000. It obviously specifies the Zarr format down at the bottom. And there's a few other things. There's the data type, there's the fill value that we didn't specify any filters, etc. And then there's the default compressor, which in this case is the BLOSK compressor. So the metadata, one of the coolest parts about Zarr is that you can like the metadata that describes all of this is human readable, and we can inspect it quite easily. Now we'll go ahead and quickly just trigger the write of a bunch of ones to this array. So now we just created a 3000 by 2000 array of just ones. And we actually, by using the square bracket and the colon here, we triggered the write of those chunks, including filtering and compressing and all of that. And now we can look at what this directory looks like. And we see there's the Z group, and inside of the top level directory is another directory called foo. So this is where the variable will be. And here we see our actual chunks. We didn't specify any specific adders. So the .z adders file is actually not there, but if we had put some metadata, maybe units or CF conventions or something like that, those would have appeared in the Z adders file as well. So this is a really simple take on what the Zarr data model is, and one of the key things to remember is that we're using the directory store here, and so we can actually inspect this on a file system. But there's actually a lot of other storage systems we can use, and you get to choose. It's one of the best parts about Zarr is the flexibility of its storage system. So we use the directory store. That's the first one in the list here. We could have used a zip file and packaged everything into a single file. Or there's a long list of other database or key value store like data formats that we could have used. At the end, I list off a bunch of cloud object stores. So Azure Blob Storage, S3, Google Cloud Storage, those are all options as well. The only criteria that that a storage system has to be able to fulfill is that it needs to be able to expose something like a key value interface. So if you're a Python user, that could be anything that looks like a dictionary, where the keys are strings and the values are bytes. And the storage model is really built around this idea that is anytime, so long as you can get your keys, could be the chunk ID 00, for example, or a metadata file like Z group. As long as you can get your keys into strings and your values into bytes through a compressor, then you can use that as a store. So I'm going to get a lot of examples on this in a second. I'll just provide two. In the first example, I'm just going to take that example one Zarr directory store, and I'm going to zip it up. So I'm going to create a zip file of that whole directory. That's what this top line does. Don't worry about that. The main thing you need to know is that we end up with a new file called example1.zip, and we can open that up with a zip store and open the root group and actually pull the array out foo that we created a few slides back. So that's an example of using the zip store. I don't have example one on Google Cloud Storage, but we do have the CMIP6 data set there. And so here is an example of connecting to a cloud object store and opening the HFLS variable. And in this case, we see the dimensions are 1800 by 192 by 288. So that's another way. There is a very long list of potential storage mediums to use. The goal of this talk is not to show you all of them, but we will highlight a few more as we go. Another thing that Zarr provides is what we call pluggable compressors and filters. So Zarr exposes a collection of compressors and filters through the num codecs library. And this is just a common set of compression codecs. We already saw BLOSK a couple times, but there's also zlib and bz2 and lzma and zfpi, a whole bunch of compression codecs there. And those codecs are all provided in are all developed in a really simple interface. So adding another one is not all that hard. There's also pre-compression filters, delta, quantize, et cetera. And then integrity checks or checksums that you can also add into there. So the figure on the right is basically showing what the workflow would be. So I have my chunk 01 in memory. It's a NumPy array. You can think of it as a NumPy array. I can pass it through an arbitrary list of filters. Eventually it goes through a compressor, and then that compressor is written to this storage layer as a key, a string 01, and a binary string of bytes. So that's how the pluggable compressors and filters work. Here's an example of using a filter, or sorry, a compressor. Here we import the BLOSK codec from num codecs. We're going to create a new directory store. In this case, we're going to create a pretty, I'll call it a fairly big array. And we will add our kind of customized BLOSK compressor here to the last line of our zeros command. And if I were to trigger the write on this with or without compression, my machine would probably have a bit of a problem writing the 35 petabytes that is the array here. But just to repeat my point from earlier, Zarr only writes chunks with actual data in them. And so long as I don't, I can create very large arrays without having to actually write the data. So the last thing that I wanted to highlight on kind of on the data model is that it's defined by a community developed and open specification. So the specification is actually human readable. You can go on to the Zarr website and click on the Zarr storage specification version 2, which is the current version. and you can read about it. And it's actually not that complicated, and you could gain some deeper understanding about how it all works that way. So another thing I said that Zarr can do is parallel reads and writes. So Zarr arrays can have multiple concurrent readers. They can have multiple concurrent writers. They can do that via multiple threads and or multiple processes at the same time. The one caveat here is that it depends on the store. So the store has to be able to support multiple concurrent readers and writers, but the Zarr data layout itself, the format, doesn't preclude any of those things. In Python, we often use the Dask library for parallel computing with Zarr, but there have been applications that have used MPI and other parallel computing frameworks as well. So by no means is Zarr tied to Dask. It's if you're doing analysis in Python, though, it's probably the first thing you should try. There are, I mentioned that the Zarr Python library is the kind of initial and reference implementation of Zarr right now, but there are implementations in multiple other languages. This is a non-exhaustive list, but there's a Java implementation, a C++ implementation, Julia, and JavaScript. And I'll cover in a little bit that there's also a recent custom implementation for in Net Cdf. My goal was to not spend too much time talking about X-ray, but X-ray is actually how I, as a Zarr user, interact with the Zarr format and library most commonly. So X-ray is an open source Python library for in-dimensional labeled arrays and data sets. It's built around the Net Cdf data model. And it was one of the first libraries to support the Zarr data format and to utilize the Python implementation. So what I'm showing here in the bit of tutorial code is we import X-ray, we load a data set from the tutorial data set called RASM, and we write it to a Zarr data set. So I don't show you exactly what this looks like yet, but we write a Zarr data set out, and then we just read it back in from the directory store rasm.zarr, and we see that we get a data set with one data variable, t_air, 3 coordinates, time, xc and yc, and 3 dimensions. So this will look very familiar to Net Cdf to you. And if you're an X-ray user, you can move back and forth between the Net Cdf file format and the Zarr format seamlessly here by just changing out the data set that you point to on disk or on the cloud. So just want to really highlight that if you want to start working with Zarr a little bit, X-ray is a great way to start doing that. We can easily move data back and forth between Net Cdf and Zarr, and it's a really nice way to get started. The next part of this, I want to talk a little bit about how Zarr works in the cloud, and recognize the cloud is not something that most people on listening here spend a lot of time working in, but it's becoming more and more of a part of the way data moves around the world. And so I thought it would be useful to focus on a little bit. So Zarr was from the very beginning designed to take full advantage of Cloud Object Store, and as opposed to a file system that's a POSIX-like file system where there's a file table that is maintained. Object Store is more of a bucket with keys in it, and the keys in the bucket are not necessarily organized in a meaningful way. So the way you get data out of object store is over HTTP calls. So it's more of a web interface. And with the way Zarr takes advantage of this is that the bytes are chunks or metadata, and they're read and written via HTTP calls directly. Something to keep in mind about when using Cloud Object Store is that for any individual operation, there's actually quite a bit of overhead, but the cumulative total bandwidth, when you parallelize over access to many objects at the same time, the bandwidth is really high. So that's for those of you coming from a parallel file system, you'll recognize that the individual object retrievals there's quite a bit of latency, but the total throughput can be much higher than a parallel file system. We use Zarr regularly on the cloud via public cloud object storage interfaces, so Google Cloud Storage, S3, Azure Blob Storage, etc. But the interface works on on-prem hardware as well via Ceph or other web server-like interfaces. There are about well, there's two main CMIP6 data sets on the public cloud right now. The first one is the CMIP6 data set on Google Cloud Storage, and the second is on AWS. There's a link at the bottom of the page right now that will tell you more about that, but there are tens to hundreds of terabytes of the CMIP6 archive that have been converted to Zarr format and published in the public dataset programs of both of these cloud providers. So obviously a lot of folks at NCAR work with this data set, and this is another good way to get started with Zarr because somebody's already done the hard work of pulling the data from ESGF and then publishing it via these two clouds. Another data set that's been published on, this time just on AWS, is the CSM large ensemble data set. So this one, I worked with Jeff DLB and Anderson Bonahauer, excuse me, I butchered Anderson's last name, but and Kevin Paul, and we published about 100 terabytes of the Lens data set to S3. And on the right, you're seeing an example where we're reproducing a couple figures from the first analysis of the CSM large ensemble. Here we're using the Pangeo cloud infrastructure. We're using Xarray and Dask and Zarr to process the data. And if I talk slow enough, in about another 30 seconds or so, there will be a plot that comes up of one of the from this K et al. Paper. What we're seeing is the Dask scheduler doing a bunch of processing here. So all of the different tasks are being processed in parallel, and we're processing a few dozen terabytes of data here in just a few seconds. See if I can skip the video ahead a little bit. All right, there you go. I wasn't able to spend 2 minutes on this on this intro, but there you go. Okay. Zarr recently landed support within the Net Cdf C library. So this is a new feature addition to the Net Cdf C library. The Net Cdf 4 interface had adopted the HDF5 data format as its container object. And with the addition of Zarr, there's another option for how to access how to store data with Net Cdf. So this is a really new data format within Net Cdf, and it doesn't have full support right now for the Net Cdf API. Importantly, they're working on things like unlimited dimensions and filters and parallelization. Supposedly really soon, the Python implementation of Net Cdf 4 will be able to access data on S3. And it's really just a packaging issue at this point, is my understanding. So put that one in your like coming soon characterize that one as coming soon, but all the feature development on that should be there. So I'm going to move into kind of the highlights of a few other applications of Zarr. I wanted to call out a SciParks project from 2019 that used Zarr via a C++ library called Z5 within CESM. So in this project, they replaced the Net Cdf and parallel Net Cdf MPI workflows with a Z5 with compression workflow for writing data out of CESM. And they found some interesting preliminary results. They found that parallel Net Cdf with no compression coming out of CESM was still the fastest. But if you wanted compression, comparing Net Cdf 4 with compression to Z5 with compression, found that Z5 or Zarr was quite a bit faster. So this is really encouraging results to see on an HPC style workload, where the parallel file system kind of is different, provides a different set of obstacles than what we would find in, say, cloud computing environments. So the link to this SciParks project is down here at the bottom, and if this is something that you're interested in, it's worth checking out the results from this. Have a few kind of more far out ideas of what Zarr is allowing us to start thinking about. In particular, a couple of projects I've had the chance to work on over the last couple of years, things that Zarr is kind of opening up. They're like, oh, I wonder if we can do that sort of thing. So I thought I'd highlight a couple of those. The first is using Zarr as a data object for streaming data out of simulation models. So we wrote a blog post about this in early 2020, where we started to experiment with the idea of writing, instead of writing data to disk, instead streaming it to a distributed database. In this case, we used Redis to do our analysis on the fly. And so we set up a really simple example using Conway's Game of Life, where our simulation model was Conway's Game of Life, and the data from that model was streamed through the Redis database to our client code. In this case, we were using Python. And so if streaming data out of climate models, for example, is of interest to you, this one might be something worth checking out. Another thing that Zarr has got us thinking about is using it as a web API for publishing data. And one of the really cool things, in fact, it's very similar to what OpenDAP does, where data endpoints are exposed, and then Net Cdf-like data can be read over network requests. In this case, we can use Zarr data published as either a REST API or just a web server. And we've been experimenting with what it would look like to do this at scale and at performance, in a highly performant manner. So again, wrote another blog post, and there's actually a library called XPublish that does this. There are a few other places that people are publishing data via web APIs as well, via Zarr. Okay, so the final bit I have here is just that the version 3 of the spec is currently under development. So like I said at the beginning of this talk, there's a key part of the Zarr project is that the spec itself is community developed, and it's being coordinated on GitHub. So this is just a screenshot of the initial set of changes to the core protocol. And so anyone can go there. It's on GitHub at Zarr developers/Zarr specs. And a few things that are being discussed and added to the spec are specific specifications around distributed storage and how keys are listed and managed and tracked in stores. Focus on interoperability. The fact that the Zarr was developed using the Python library as its reference implementation has meant that interoperability among other languages is something that you have to keep a close track on, as well as interoperability across versions of the specification. An extensions framework is being developed to allow for custom filters, maybe named dimensions, custom data types, etc. And there are a few other pieces to the spec that are being added. The last one that I wrote down here is an abstract store API that defines the characteristics of a store. So just wrapping up here a little bit, if you're just joining us, Zarr is an open source format for the storage of chunked compressed ND arrays. Guessing you're not joining us now though. So to just highlight what I went over, we covered the data model and how Zarr data is laid out within a store. Covered a bit about the specification and the Python API. Specifically covered how the Python API breaks out different storage layers and compressors and filters. And then I talked through a handful of applications of the Net Cdf library, the HPC via Z5, and obviously uses of Zarr in the cloud. So that is what I have. And I assume that if I think Jeff has questions, or he's going to be reading me questions, and I'm going to be responding. So thanks for listening, and happy to take questions.
Great. Well, Joe, thank you very much for this very informative talk and for taking the time to do it remotely from Seattle. Sorry that we couldn't fly you out here for an in-person seminar.
All good.
We do have a few questions in the Slido, and if anybody wants to add some now, please go ahead and put them in soon. You can also upvote them just like in the usual town halls. So we'll just take them in the order that they were upvoted. The first one from Davide Del Vento is, I'm not sure what you mean by limited to POSIX-like storage only, which I believe is the only but of Net Cdf/HDF. You can store Net Cdf files in Cloud-like Object Store. I've done it, but you may have something more specific about that. If so, what is it?
Yep. Yeah. So with the for Net Cdf and HDF specifically, they're really built around the idea of a file system being present, and you can definitely kind of fake it. And in Python, there's ways to do it, and obviously, there's no reason you can't store you can store any type of file in S3, but efficient reads are difficult when you have to seek around the file to find bytes. And so having one of the things that from an architectural standpoint Zarr does is it doesn't require you to seek to find a new chunk of data. Instead, the keys are stored as separate objects. So that's mostly what I mean there. Yes, absolutely. You can use Net Cdf in the cloud, and you can in Python you can get file objects and read data from them. But it's not particularly performant because of the lack of kind of file system operations like seek.
Okay, great. Davide, I hope that answered your question. The next one actually was submitted by me. Sorry.
Well, hi.
Is there any effort to provide more comprehensive information in the Zarr metadata files, i.e. not just describe the structure of the chunks, but also metadata to support discovery and reuse? Yep.
There's the answer to that is yes, but it's probably not going to happen at the specification level. I think there's people thinking about that, but in that case, for that sort of application, there's nothing really different about Zarr from any of the other containers with metadata in them, like NetCDF or HDF. It's really up to the user or to the data provider or whoever it is to curate the metadata in those data sets to support that. So there's certainly conversations I could point you to about the sort of things that people put in, that are thinking about putting in the metadata attributes on these data sets. But in that case, I don't think it's particular to Zarr. I think it's just how we think about, multidimensional self-describing data.
Okay, great. Next question submitted by Doug Schuster. How well does Zarr support existing download to and analyze on my local computer workflows? It seems that pre-built Zarr stores may be fairly large to download if they are structured to effectively support data proximate analysis on their host systems.
Yep. So I think, if I understand Doug's question, the question is whether or not, say, I have data sitting on S3, maybe it's a big chunk of the CMIP6 data set, but I actually don't want to do my compute on AWS. I want to do my compute on my local computer. How does that work? And the answer is it works as well as you can move data across the internet. There's benefit to doing data proximate computing and not doing your computation right next to the data. But I've actually found it to be quite performant to point at a remote Zarr store and do the compute either on my local computer or even from another cloud system. So for example, I've been pulling data from Google into a VM on Azure, and that works just fine. So you can do it. It doesn't necessarily have to follow the download model, though. You don't necessarily take the file and write it to your local file system. You can usually just stream your computation.
Okay, thank you. See, next question by Andrew Bennett. How does Zarr work with newer or non-traditional data types like dual numbers or posets? I don't even know what that is.
Posets, yeah. Yeah, it's a good question. There is an extension in the that's being developed for the v3 spec for custom data types. And I think the answer is that needs to be finished before custom data types will be supported. There are, if you're just using Zarr Python, you can put an object D type into chunks, and you can put anything in those, but interoperability is not supported in that case, to say C++ or Net Cdf C, something like that.
Okay, thank you. Let's see, Davide, I guess, has a follow-up. He had the first question. Thanks, that clarifies things. Given the huge legacy of existing NetCDF HDF files, I was wondering why an augmentation of the format to support the cloud use case rather than creating a whole new format. Full disclosure, I believe we already have too many, so I hate to see a new one.
Yep. Yeah, absolutely. So so I think if the NetCDF team was here, they would make sure to say that the Net CDF part of the Net CDF HDF combination there is the data model, and the HDF is the file format. And you know, the HDF team is working on their own cloud support. And it's, you know, when Zarr started, there was really an open question of what the architecture was for doing cloud performant multidimensional array storage. So I think the Zarr team, you know, certainly when I got involved in the project, it was what will work. We don't know exactly yet what will. So it was an experiment. I think that there's room for all of these, and I think they'll all continue to fill their space. On certain architectures, the Net CDF HDF model is going to work really well. But as the cloud cloud applications grow and grow, I think that purpose-built storage formats are going to become more and more amenable to the type of workflows we do. So I definitely hear Davide's point that proliferation of more and more storage formats is not necessarily something we want to see, but I think there's at least room for one more.
Okay. Let's see, next question from Helen. How backwards compatible is Zarr? Will Zarr 3.0 read Zarr 2.0 files?
I think the answer is yes. I don't know that for sure though, and I can follow up on that. But I think that the specification is growing, but not. I don't think there are serious breaking changes in how the layout of the data is represented.
Okay. Let's see. Haiying asks, I heard that I can manually zip a Zarr file and can open from Zarr by zip store, but I tried that, it doesn't work. Has anybody tried that in the Zarr group before?
Yeah, it's actually the example I used was a directory store that I zipped up and opened with the Zarr Zarr zip file store. So definitely possible. Easy to get the hierarchy a little wrong in a zip store and putting the keys one level up or down. So I'm happy to send you the little snippet of code I used. Might be useful to you.
Great. Yeah, I'm sure that would be useful. Another question that I submitted, does the Net CDF Zarr support mean modelers will eventually be able to get the benefits of Zarr without worrying about the format details?
Yeah, absolutely. I think that that's one of the main reasons we're so excited about the Net CDF API developments is that we should be able to both access data that's already stored in Zarr via the Net CDF library without having, with existing tools. There's quite the ecosystem around Net CDF. And so being able to leverage Zarr and that ecosystem simultaneously will be really important. But also being able to write Zarr formatted data from previously built applications. It might be climate models, it might be analysis code, but that will be a big win as well.
Great. And I might add that I believe the HDF group is hoping to actually charge licensing fees for HDF5. I don't know if they're still doing that, but I know that was an issue a little while ago.
Yep.
Let's see, Supreet Suresh asks, could you point us to an example of using C++/Fortran, not sure if it supports Fortran, interface of Zarr, a simple read and write?
Yep. I don't have one handy that I could drop in the chat right now, but I'd be happy to follow up. My understanding is the Fortran Net CDF interface is built on top of the Net CDF interface, so it should have inherited the Zarr support with the last release. So it should all be there. So it's just a matter of getting the right code snippet for you. I did really try hard not to put any Fortran in my talk, which I think that most people will appreciate.
I don't know, in this audience, you know.
I know, I'm trying to make the world the one I want to see.
Yeah, okay, Let's see, Gretchen Mullendor asks, it seems that defining the keys is key to better performance. Is that correct? I.e., bad organization by data manager could take away advantages of Zarr.
Absolutely, absolutely. So another way to put that is the way that you break up the chunks inside of your array is needs to reflect the way your data access will be. If you just think about a 2D array of column major versus row major, if your access pattern is orthogonal to your chunk layout, you'll have to read all chunks to access, all rows to access a single column or vice versa. So very, very important, especially in higher dimensional data. And what we found is that there's often times where a single chunk layout is not amenable to all applications. So that's no different than any other chunked array storage. If you're using HDF5 or something like that, you also choose the chunk size or use the default. But the access pattern problems are the same. Zarr just makes those a little more apparent because the keys are split out explicitly.
Okay, that's a good point. We're getting chunking without even really knowing it, and not necessarily the best chunking.
Yep.
With these other, okay. All right, there's a couple of comments. I guess there's, let's see, Rich commented, this was very early in one of your slides, isn't 20 petabyte 2 times 10 to the 16, not 2 times 10 to the 17?
I don't have the slide in front of me anymore. It's possible I had a misaligned arrow on this one. So I'll give that a check.
Okay.
Rich is always watching the details.
Yeah. Okay. And then last two are just comments. Davida says, great talk and great discussion. Thanks, Joe and Jeff. And Haiying says, that'd be great, I guess, about the request for the code snippet. So
great.
I'd like to, again, thank you and thank everybody who attended. In theory, we'll do another one of these next month in July. If you'd like to be a CISL seminar speaker, please let me know, because we're always looking for speakers. And Joe, thank you once again for your time. And we're going to end now. Although, Joe, we do ask you stay on a few minutes.
Great.
Part. Yeah. Okay.
All right.
Thanks, everybody.
Cool. Thanks.